Welcome to the SAR channel, where sound and audio are demystified. In many ways, digital signal processing, DSP, brings us back to the basic ideas behind digital audio. While conversion, error correction, data reduction, and other steps are important in a digital system, the real core is the software-based processing of the audio data itself. If we could not change or work with the numbers that make up digital audio, digitizing sound would not be useful in most situations. DSP also reconnects us with the basic math that digital audio is built on. At the same time, DSP goes far beyond simple logic circuits and relies on advanced algorithms to handle signals efficiently. In addition, digital signal processing often requires special hardware to operate properly. Digital signal processing is used to create, study, modify, or otherwise work with signals in digital form. It relies on sampling and quantization, the same ideas that make digital recording possible. But instead of storing or sending the data, it focuses on processing it. DSP is like the technology used in computers and microprocessors, but instead of handling general data, it deals specifically with signals. A digital audio signal is a sequence that changes over time, and its order must be preserved for it to be understood or processed correctly. In simple terms, DSP applies a mathematical formula or algorithm to change the numbers in a digital bit stream. A signal can be any natural or man-made event that changes with time or another variable. Signals can be represented in analog or digital form, and each has strengths and weaknesses. Working with digitally sampled waveforms provides advantages over handling continuous analog signals. Using clear, discrete samples allows for components with looser tolerances, predictable accuracy, perfectly repeatable circuits, the ability to apply many operations to a sample, and reduce sensitivity to noise, temperature, or aging. Because discrete time signals are programmable, their behavior can change without altering hardware. Digital chips are small, reliable, inexpensive, and capable of complex tasks. Some functions are easier or only possible digitally, such as linear phase filters, long-term stable memory, adaptive systems, image processing, error correction, data reduction and compression, and converting signals from the time domain to the frequency domain using tools like the DFT or the FFT. However, DSP also has drawbacks. It always needs power because no passive digital circuits exist. It cannot yet handle extremely high-frequency signals. Digital versions of signals may require more bandwidth than analog ones. DSP systems are costly to design, and they need hardware that can perform fast calculations. When used with analog signals, AD and DA conversion is necessary. Very weak signals, like from an antenna, or very strong ones, like those driving a speaker, can be challenging to manage, so DSP systems need proper amplification before processing. In the 1960s, signal processing was done with analog methods, using electronic and mechanical systems to work with signals in continuous time. Digital computers were not yet powerful enough to handle digital signal processing. But in 1965, the creation of the fast Fourier transform, an efficient way to compute the discrete Fourier transform, along with faster computers, helped launch the development of modern discrete time mathematics and today's DSP technology. Digital signal processing is now used in many fields, including soil testing, oil and gas exploration, radio and radar astronomy, telecommunications, data communication, medical equipment, image processing, TV production, filmmaking, scientific instruments, the chemical industry, and more. DSP has transformed professional audio by improving effects, device communication, user control, and computer-based operation. DSP also offers huge possibilities for audio work. It can handle error correction, multiplexing, sample rate conversion, speech and music analysis and synthesis, data reduction and compression, filtering, adaptive EQ, dynamic compression and expansion, reverberation, ambience creation, time alignment, noise cancellation, mixing and editing, encryption, watermarking, and acoustic measurement, all through digital processing. Digital audio signal processing works by manipulating audio samples, and because these samples are stored as numbers, DSP is essentially a form of mathematical calculation. So, understanding audio DSP starts with understanding its mathematical basis. A signal defined only at specific, separate points in time is called a discrete time signal. According to the sampling theorem, any band-limited continuous signal can be represented as a discrete time signal without losing information in theory. Although both discrete time signals and digital signals are made of samples, a discrete time signal can have any real numerical value, while a digital signal is limited to a fixed set of possible values. In digital audio, this limitation means the signal must be approximated through quantization. A discrete system is any system that takes one or more discrete input signals and produces one or more discrete output signals based on certain rules. Both the input and output signals are sequences of numbers. Two key qualities of discrete systems are linearity and time-invariance. A linear system follows the rule of superposition. If you add input signals together, the output will be the sum of the outputs those signals would produce individually. It also follows homogeneity. The output scales in proportion to the input. A linear time-invariant LTI system always behaves the same way over time. A discrete system is causal if its output at any moment depends only on current and past input values, not on future ones. In simple terms, a causal system produces no output before receiving an input, and the output never depends on inputs that haven't occurred yet. The impulse response is a key idea in many fields, including digital signal processing. It completely describes a linear time-invariant discrete system in the time domain. Like any discrete system, an LTI system turns an input signal into an output signal, but it has a special feature. If you feed it an impulse, a delta function, the output you get is its impulse response. This impulse response shows how the system behaves over time, and from it you can also determine the system's frequency response. Most digital filters are LTI systems and follow this rule. A system is stable if every input of limited size produces an output of limited size. In simple terms, when you combine the magnitudes of all inputs with the impulse response, the total must remain finite. Useful DSP systems are stable. The sampled impulse response can also be used for filtering. Individual audio samples can be seen as impulses expressed as numbers. To filter a signal, each sample can be used as a scaling factor. Every value in the filter's impulse response is multiplied by each sample value. This creates many versions of the filter's impulse response, each scaled by a different sample. To form the output, each scaled impulse response replaces the sample that created it. Because the impulse responses can span many samples, several of them overlap. Adding all these overlapping values produces the new filtered signal. This process is called convolution. The output of any linear system is the convolution of its input with its impulse response. Convolution happens in the time domain and is the time domain equivalent of multiplying frequency responses. In the same way, multiplication in the time domain corresponds to convolution in the frequency domain, a dual relationship. In convolution, sample values, representing the signal at different times, are multiplied by weighting factors. These products are then summed to create the output. A finite impulse response, FIR, oversampling filter is a good example. A group of samples is multiplied by the filter's impulse response coefficients, and the results are added. The input signal has been convolved with the filter's impulse response in time, producing a filtered output. To summarize, an LTI system's full response to an impulse is its impulse response. Its response to a scaled sample is a scaled impulse response. Its response to a delayed impulse is a delayed impulse response. Since input samples form a sequence of impulses with different sizes and delays, each sample generates its own scaled and shifted impulse response. By convolution, the output at any moment is the sum of all the partial impulse responses active at that time. When two waveforms are multiplied, their spectra are convolved. When two spectra are multiplied, their corresponding waveforms are convolved. An LTI system's response to any input waveform can be determined from its impulse response and the response to each piece of the input. Convolution in time corresponds to multiplication in the frequency domain and the reverse. Ultimately, any output signal can be viewed as a combination of impulses. Analog and digital systems are built on the same mathematical foundation. Whether dealing with resistors, capacitors, and inductors, or with scaling, delay, and addition in DSP, all of which are linear, time-invariant elements, these systems can be understood using complex numbers. A complex number z can be written as z equals x plus jy, where x and y are real numbers. Here, x is the real part and jy is the imaginary part. An imaginary number is simply a real number multiplied by j, where j is defined as the square root of -1. Since no real number squared gives a negative result, mathematicians invented imaginary numbers to handle such cases. The expression x plus jy is the rectangular form of a complex number and shows its two-dimensional nature. A waveform can also be represented by a complex number. The J operator lets us move between the real and imaginary worlds. A real number multiplied by an imaginary number becomes complex, and an imaginary number multiplied by another imaginary number becomes real again. Multiplying by a complex number acts like applying a phase shift. Signal processing, whether analog or digital, can be viewed in two different but related domains. Analog signals are described in the time and frequency domains, while sampled signals are described in discrete time and discrete frequency domains. A transform is a mathematical tool that allows movement between these domains. Continuous transforms apply to signals that vary continuously in time and frequency. Series transforms apply to continuous time and discrete frequency. And discrete transforms apply to signals that are discrete in both time and frequency. There are two main ways to compute an output signal: convolution in the time domain or multiplication in the frequency domain. While convolution is conceptually straightforward, using transforms and multiplying spectra is typically more efficient in practice. Transforms are also essential for analyzing a signal's spectral content. Regardless of the method, a filter's effect on a discrete signal can be determined accurately. The Fourier transform for discrete signals produces a continuous spectrum, but it is computationally demanding. For this reason, practical systems use the discrete Fourier transform, DFT, which generates the spectrum of a discrete signal as a set of harmonically related sinusoids, each with its own amplitude and phase. The DFT treats the sampled waveform as if it were an infinitely repeating signal. Its inverse returns the original time domain samples. The DFT can also be seen as sampling a signal's Fourier transform at n evenly spaced frequency points. The fast Fourier transform, FFT, is an efficient way to compute the DFT. It converts a time domain sequence, such as a filter's impulse response, into real and imaginary components in the frequency domain from which magnitude and phase can be derived. An inverse FFT returns the time domain signal. FFT filtering works by transforming overlapping signal segments, multiplying them by the transformed filter, and using an inverse FFT to reconstruct the filtered result. Because the FFT requires far fewer computations than direct convolution, it is often the preferred method. The Z-transform plays a role for discrete signals similar to the role of the Laplace transform for continuous signals. Just as the Laplace transform generalizes the Fourier transform, the Z-transform generalizes the DFT. While the DFT is used for direct numerical operations, the Z-transform is mainly a theoretical tool for DSP analysis. Key properties apply. Linear combinations in time remain linear in the Z domain. Convolution in time becomes multiplication in the Z domain. The ratio of a filter's output transform to its input transform, called the transfer function, is the Z-transform of the filter's impulse response. For an impulse input, the transfer function directly gives the output. A time shift corresponds to multiplying by Z raised to a power equal to the number of samples shifted. The Fourier transform of a discrete signal is equal to evaluating the z-transform along the unit circle in the z-plane. The unit circle is defined by the equation z equals e to the power of j theta, which traces a circle of radius 1 in the complex plane. When the z-transform is calculated on this circle, the result gives the system's frequency response. Because real systems use only a limited number of samples, they must operate within the region of convergence, ROC. The unit circle is the smallest region in the z-plane that lies inside the ROC for all finite stable signals. For a system to remain stable, its poles must be located inside the unit circle. If the poles fall outside the circle, the system becomes unstable. In summary, the transfer function of a linear time-invariant discrete time filter is the z-transform of its impulse response. The spectrum of a signal is simply the value of its z-transform evaluated on the unit circle. Writing a digital filter's transfer function in z-transform form makes it possible to analyze the filter using its poles and zeros. The zeros are the roots of the transfer function's numerator, and the poles are the roots of its denominator. Some basic points apply. Zeros come from adding input samples together, while poles come from feedback in the system. The filter's order is the number of poles or zeros it has, whichever is larger. A filter is stable only when all poles lie inside the unit circle in the z-plane. Zeros may be located anywhere. If all zeros lie inside the unit circle, the system is a minimum phase network. If all poles are inside the unit circle and all zeros are outside, with each zero and pole reflected across the circle, the system is an all-pass or constant amplitude filter. A system is phase linear when it has only zeros, other than the origin, that appear in symmetric pairs reflected across the unit circle. No real-world function can contain more zeros than poles. When a system has real coefficients, its poles and zeros always appear in complex conjugate pairs, making the plot symmetrical across the real axis of the z-plane. The nearer a pole or zero is to the unit circle, the stronger its influence on the frequency response. Effective DSP work needs advanced hardware and software, but all digital signal processing is built from three basic steps: adding, multiplying, and delaying. Adding means combining several digital values into one. Multiplying changes the level of a signal by scaling each sample with a coefficient. A time delay stores a digital value for one sample period. In real systems, these basic steps are repeated many times for every sample, arranged in specific patterns to create the desired effect. Using these simple building blocks, algorithms can be designed for audio tasks like reverb, EQ, compression, data reduction, and noise control. For real-time processing, all calculations for each sample must finish within a single sampling period. If you've enjoyed this video so far, please hit the subscribe button for more. Thank you. Filtering, or equalization, plays a key role in audio work. Analog filters, whether passive or active, shape frequency and phase based on linear time-invariant differential equations, which describe how the system behaves over time. Digital filters, on the other hand, process each sample through a transfer function to change frequency or phase. Their behavior is described by linear shift-invariant difference equations, defining how the signal evolves from one sample to the next. At extremely high sampling rates, these digital equations closely match the equations used for analog filters. Digital filters can be built from analog designs. Impulse-invariant methods work well for low-pass filters whose cutoff is far below the sampling rate. Other methods use mathematical transformations to convert analog filter behavior into the digital range, mapping analog frequencies into 0 Hz through the Nyquist limit. The transfer function reveals a filter's poles and zeros. The roots of the numerator give the zeros, and the roots of the denominator give the poles. Zeros act like feed-forward paths, and poles act like feedback paths. Following the transfer function around the unit circle shows the filter's frequency response. A filter is canonical if it uses the fewest delay elements needed for its output. Changing coefficient values changes the filter's response. A filter is stable if its impulse response fades to zero as n approaches infinity. Convolution can implement a filter directly from its impulse response. Convolving the input with that impulse response produces the filtered result. In effect, convolution plays the role of the difference equation, with the impulse response standing in for the equation's coefficients. Whether to use a difference equation or convolution depends on the filter's structure and the application. A filter that works on a limited number of samples is called a finite impulse response, FIR filter. As the name suggests, its impulse response lasts only for a finite time. An FIR filter can have only zeros, except at the origin, can achieve linear phase through a symmetrical impulse response, reacts just once to an impulse, and is always stable. Because it uses no feedback, it is called a non-recursive filter. Every non-recursive structure is FIR, but not every FIR filter must be built in a non-recursive form. To understand FIR operation, recall that large changes between samples represent high frequencies, while small changes represent low frequencies. A filter works by adjusting these differences between samples. An FIR filter can be built as a multi-tap structure that serves as a basic element for more advanced filters. To get the desired frequency response, the filter's impulse response coefficients must be designed. Simply cutting off the ends of the ideal impulse response causes aperture effects and the Gibbs phenomenon, peaks near the cutoff, and ripples in both the pass band and stop band. All digital filters have finite bandwidth. This means that real impulse responses must be truncated. An infinite ideal impulse response produces a perfect rectangular frequency response, but a finite response always shows Gibbs artifacts, not analog ringing, but the normal result of bandwidth limits. The choice of coefficients affects phase linearity. For many audio uses, linear phase is desirable because it gives a constant delay across frequency and a symmetrical output. The impulse length needed depends on the target frequency response and ripple limits. It is important to smoothly transition between useful and non-useful samples. In many designs, the coefficients are multiplied by a window function, which is a finite weighting pattern that shapes the ideal Fourier coefficients into a practical form. The window's own frequency response shapes the final filter. Because multiplication in time equals convolution in frequency, applying a window in the time domain is the same as convolving the spectra. Examining the DFT of the window reveals its effect on the filter's response. DSP often works with a limited set of samples taken from a longer signal, and this truncation causes side effects. Using a window function reduces these problems, but also affects the filter's transition bands. For instance, a rectangular window simply gates the signal. Its length must be an integer number of input periods, so the signal must repeat exactly within that span. When this condition is met, the window's spectral nulls align with the signal's harmonic spacing. When it is not met, the nulls no longer match the harmonics, causing spectral leakage. Other windows reduce leakage by tapering smoothly to zero at the edges, limiting energy outside their main lobe. Another design method is to sample the desired response, compute its DFT, and relate those values to the needed impulse response. The impulse response is then found from the inverse DFT. A further approach is to set up optimal conditions and use an algorithm to find coefficients that best approximate the desired response with minimum error. In a general difference equation, the output depends partly on earlier output values. These delayed feedback terms create a recursive filter, and they appear in the denominator of the transfer function. Some feedback settings can make the filter unstable. Each pole adds an exponential component to the impulse response. Because the output is fed back into the input, the response theoretically never reaches zero, meaning the impulse lasts indefinitely. This kind of filter is called an infinite impulse response IIR filter. An IIR filter can contain both poles and zeros, introduces phase shift, and may become unstable if any pole is on or outside the unit circle. Typically, an all-pole filter is an IIR filter. IIR filters cannot produce linear phase. Their impulse response is not symmetrical, except when all poles lie exactly on the unit circle, which can happen when the filter is made from several first-order sections in series. Since the IIR output is fed back into the input with scaling, it is termed a recursive filter. All IIR filters use a recursive structure, but not every recursive structure produces an IIR filter. Any feedback loop must include a delay element. Otherwise, the filter would need to know a sample value before it is actually computed, which is impossible. Overall, it is simpler to design FIR filters that are stable and have linear phase than to design IIR filters with those properties. However, IIR filters can create a much sharper cutoff than an FIR filter using the same number of coefficients. FIR filters need more stages and more computation to match that performance. As with any digital system, noise and numerical errors must be considered. A filter's design, structure, arithmetic, and coefficient choices determine how much error appears. Digital filters are more flexible than analog filters, which have limited operating ranges. However, they require significant computation, especially for swept equalization. When the center frequency changes, new coefficients must be calculated, which is not simple. To avoid quantization noise, sometimes called zipper noise, filter and amplitude scaling coefficients should ideally be updated at the sampling rate, though in practice, updating at half or a quarter of the sampling rate is usually enough. Linear interpolation is often used to compute these coefficients. The range must be controlled so filter poles don't temporarily move outside the unit circle, which would cause temporary instability. Adaptive filters adjust their parameters automatically based on optimization rules. They do not have fixed coefficients. Instead, the values are calculated in real time. An adaptive filter includes both a filter section and a control unit for computing coefficients. Many adaptive algorithms aim to minimize the difference between the filter output and a reference signal. Although any filter type can be used, adaptive filters often employ transversal, lattice, or ladder structures. They are commonly used for echo cancellation, noise reduction, adaptive line equalization, and prediction. A transversal filter is an FIR filter where the output depends on the current input and several previous input values stored in memory. Each input is multiplied by a coefficient and summed at the output. Only input values are delayed. There is no feedback, making it a non-recursive filter. This structure is widely used for low-pass filtering with oversampling. In practice, digital oversampling filters often use a cascade of FIR filters, each operating at a sampling rate that is a power of 2 higher than the previous one. The number of delay elements, taps, in an FIR filter determines passband flatness, transition band slope, and stop band rejection. Many digital filters are implemented as dedicated chips, but general-purpose DSP chips can also run custom filter programs. Digital signal processing can introduce noise and distortion if precautions are not taken. Common errors include coefficient errors, limit cycles, overflow, truncation, and round-off errors. Coefficient errors happen when values are not specified with enough precision. For example, processing 16-bit audio usually needs 24-bit or higher resolution. Limit cycle errors can occur when a filter's output decays after a signal is removed, sometimes causing constant oscillation. This can be prevented by offsetting the filter output so truncation produces 0. Overflow occurs when a calculation exceeds the register size. In wraparound, adding 1 to the maximum positive 2's complement number produces the maximum negative number, which could cause a loud pop on speakers. To avoid this, saturating arithmetic or sufficient digital headroom can be used, resulting in controlled clipping instead of a sudden jump. Truncation and round-off errors happen whenever the word length of a calculation is limited. Errors accumulate both during computation and when reducing word length for output through a DA converter. Hardware often limits the output word length, causing quantization-like errors. Multiplication itself does not introduce error, but discarding extra bits does. Unnecessary intermediate dithering should be avoided. Rounding after multiplication, instead of truncating, limits peak error to half an LSB, but round-off errors still accumulate over many calculations. Also, dither added at earlier stages can be lost when reducing word length. For example, a dithered 16-bit signal processed in 32-bit precision and then truncated back to 16 bits could lose dithering. To prevent this, digital dither should match the resolution of the next processing or recording stage. Digital dithering works by adding a pseudo-random number to each sample and then rounding the least significant bit to the nearest quantization level. This modulates the least significant bit and provides the linearizing effect of dither. Different pseudo-random numbers are used for each audio channel. To mimic analog dither, 2's complement values can be used to create a bipolar zero-mean signal. Noise shaping may also be applied. Errors affect both audio samples and system calculations, such as filter coefficients. Poorly defined coefficients can make a stable IIR filter unstable. Quantizing filter coefficients, however, generally does not affect linear operation or create time-varying artifacts. The impact of coefficient errors depends on how many coefficients define each pole and zero. Fewer coefficients reduce sensitivity, but when poles and zeros are widely spaced, errors have a larger effect. A DSP chip is a specialized processor that performs digital signal processing using software algorithms. These chips often work independently of a host CPU and are designed specifically for tasks in numerical and spectral processing. When memory and input-output circuits are included, the chip becomes a complete digital signal processor. A general-purpose DSP chip is programmable with software and can handle many types of signal processing tasks. Alternatively, a custom DSP can be built for a specific application. Digital audio processing requires long word lengths and fast operation. To avoid distortion from rounding errors, the internal word length of the DSP must be 8 to 16 bits longer than the input or output word. For high-quality audio, this means internal processing typically uses 24 to 32 bits or more. DSP chips often use pipelining, allowing multiple instructions to be processed at the same time. For instance, fetching an instruction from memory, decoding it, reading operands, and executing the operation can all overlap and effectively complete in a single clock cycle. A pipeline manager, along with skilled programming, helps maintain efficient processing. Like all computers, DSP chips consist of input-output devices, an arithmetic logic unit, a control unit, and memory, all connected by buses. Early computers used a single bus shared for data, addresses, and instructions. DSP chips, however, need to perform many operations quickly for real-time tasks. To achieve this, they use parallel bus structures such as the Harvard architecture, which stores data and instructions separately and transfers them on separate buses. DSP chips are built using two types of arithmetic, fixed point and floating point, which determine the data format they handle. Fixed point chips work with binary integers in 2's complement form, while floating point chips handle numbers with a mantissa and exponent. Fixed point chips have a limited dynamic range based on word length, so data must be scaled carefully to avoid overflow, which makes programming more complex. Floating point chips, using a scientific notation format, allow a much larger dynamic range without overflow, though their resolution is limited by the exponent length. When choosing a DSP chip, programmers consider cost, programmability, implementation difficulty, software support, legacy software availability, time to market, marketing factors like 24-bit versus 32-bit, and sound quality. Programming style and the hardware platform both affect audio quality and cannot be ignored. Standard PC processors can handle both fixed point and floating point calculations. The most common DSP chips in audio products are 24-bit fixed point, 32-bit fixed point, and 32-bit floating point. Each type has advantages and disadvantages for audio quality. A 32-bit fixed-point chip typically produces better quality than a 24-bit fixed-point chip running the same algorithm. However, architectural differences and optimizations can make a 24-bit chip outperform a 32-bit chip. Some 24-bit chips have hardware accelerators or support double precision arithmetic, which can enhance sound quality. By combining two 24-bit numbers into a 48-bit integer, high-fidelity processing is possible. Manufacturers often provide optimized and unoptimized versions of algorithms so users can balance cost and quality. Some 24-bit chips using double precision processing are marketed as 48-bit DSP, where high-order bits handle headroom, low-order bits store fractions, and the rest represent the audio sample. The instruction set also affects performance. Comparing fixed-point and floating-point chips is complex. Fixed-point chips trade off between round-off error and dynamic range, while floating-point chips mainly have errors from coefficient precision. Floating-point chips are easier to program, often using higher-level languages like C++, and offer a very large dynamic range. However, code from high-level languages may be less efficient than handwritten assembly, using resources that could improve audio quality. For reference, a 24-bit fixed-point chip has a 144 decibel dynamic range, 32-bit fixed-point has 196 decibels, and 32-bit floating-point provides 1,536 decibels. While 1,536 decibels is excessive for audio, it ensures the noise floor stays far below the signal. Proper programming can make both fixed-point and floating-point chips deliver excellent audio quality. Advanced techniques like double precision 64-bit processing, where available, can further improve fidelity. If you've learned anything new so far, please like the video. It really helps the channel grow. Thank you. DSP programming allows the creation of powerful and flexible audio applications. The DSP chip executes software instructions using audio samples as input. While a chip's architecture defines its potential processing power, actual performance also depends on its instruction set. DSP chips often use assembly language, which is very efficient. Higher-level languages like C++ are easier to use, debug, and document, and they work across different hardware. However, they are slower and cannot fully use the chip's specialized hardware. Assembly language, on the other hand, runs faster, uses less memory, and takes advantage of special hardware features. Its downside is that it is harder to program, read, debug, and is specific to the chip. An assembly program uses the chip's instruction set to perform specialized signal processing tasks. These instructions are generally divided into 4 categories: arithmetic, program control, memory access and transfer, and input-output. Instructions are written with mnemonics and reference the data they operate on. Often, DSP chips run in a larger host environment, where front-end programs are written in higher-level languages, leaving assembly programming for the core audio tasks. A key operation in DSP programming is the multiply-accumulate-MAC command. Many algorithms require multiplying 2 numbers and adding the result to a previous sum. DSP chips have a hardware multiplier accumulator that can perform this in a single cycle, allowing operations like sum of products or iterative calculations to run efficiently. The skill of the programmer is crucial for a successful DSP application, and software development often costs more than the hardware itself. To help, manufacturers provide libraries of common functions such as FIR Filters and Windows. Developers use various tools: text editors to write code, assemblers to translate assembly code into object code, and compilers for higher-level languages. A linker combines all object code and libraries into an executable program. Simulators emulate the DSP on a host computer, and debuggers help find low-level errors. DSP operating systems are also available, offering programming environments similar to general-purpose processors. DSP chips can handle a wide range of signal processing tasks, but digital filtering is one of the most important and commonly used functions. Texas Instruments DSP processors are designed for fast, real-time signal processing in audio, communications, and embedded systems. Their architecture focuses on efficient multiply-accumulate operations, fast memory access, and flexible instruction pipelines to handle heavy computational tasks without delays. Many Texas Instruments DSPs include hardware accelerators, dual data buses, and DMA systems to move audio samples and coefficients smoothly. They support both fixed and floating-point arithmetic, letting developers balance precision and efficiency. These features make Texas Instruments DSPs ideal for complex filtering, multi-channel processing, and other demanding audio applications where speed and accuracy are essential. Motorola processors are commonly used for DSP tasks like filtering. They are efficient because they can perform multiply-accumulate operations while loading the next set of values at the same time. Additionally, hardware do loops and repeat instructions make it easy to repeat these operations automatically, speeding up processing. Digital audio processing requires handling large amounts of data, which makes it very demanding. DSPs are designed to handle these tasks efficiently, with parallel processing to manage multiple tasks at once, like multi-channel audio, while keeping data flowing smoothly to avoid bottlenecks. The SHARC DSP architecture is a good example of hardware optimized for audio processing. Intermediate calculations need higher precision than the audio signal itself. For instance, simple 16-bit processing isn't enough for a 16-bit signal unless double precision is used. Rounding, truncation, overflow, coefficient errors, and limit cycles can all reduce signal quality. SHARC chips are designed to maintain high precision and avoid artifacts in 20 or 24-bit audio. SHARC processors handle 32-bit fixed point, 32-bit floating point, and 40-bit extended floating point operations natively using 32-bit filter coefficients. They can switch between fixed and floating point processing in a single instruction cycle, reducing the need for slower double precision math and saving computation time. DSP goes far beyond basic filtering and is used in many audio applications. Using core operations like multiplication and delay, effects such as chorusing and phasing can be created. Reverberation shows how much digital processing can manipulate time. It can mimic real acoustic spaces or generate sounds that couldn't exist naturally. Digital mixing consoles combine many DSP functions into a single system, and DSP is also essential in algorithms that remove noise from audio signals. A delay effect uses a simple storage unit, like a memory slot. An audio sample is stored in memory and then played back after a set amount of time. Reverberation depends on delay, loudness, and frequency response. In a room, delay comes from its size, while loudness and frequency response depend on the surfaces and materials. Digital reverberation can control these factors in an audio signal to create different acoustic environments. Since real reverberation involves many sound paths, a digital system must process many data elements to simulate it. Designing a digital mixing console is complex because it acts like a massive DSP system handling billions of instructions per second. While digital technology avoids many analog problems, even simple audio tasks often require advanced digital circuits and real-time processing. Creating a digital version of analog components needs rethinking old designs and using innovative digital techniques. A digital console still performs the three main tasks of any mixer: gain control, mixing, and signal selection, routing, but digitally, these tasks are more complex. Gain control requires a potentiometer, an AD converter, and a multiplier to adjust digital audio. Mixing uses a multiplexer and accumulator instead of analog resistors and op-amps. Signal selection uses a demultiplexer and encoder rather than a multipole switch. All these processes must happen on every audio sample in real time. Processing requires high speed and long word lengths, though filter coefficients can be stored in ROM, usually needing only a few thousand values. Physical controls on a digital console are just remote interfaces for the processing circuits, so no audio passes through them. This allows functions to be assignable, letting fewer controls handle multiple tasks. The console's layout is flexible. A central control section can access any assigned function, and physical controls on a channel can perform different tasks, showing their values on displays. Setup is managed via a keyboard, with configurations saved in memory or presets for quick changes. Soft signal paths allow multiple presets such as tracklaying, mix down previous settings, or a fail-safe mode. Video displays show graphical representations of signal blocks, their order, and settings like delay, filter, EQ, dynamics, fader levels, mute/solo status, phase, phantom power, and other parameters. This visualization helps operators manage complex mixes efficiently. Loudspeakers are not perfect. Their uneven frequency response, limited dynamic range, frequency-dependent directionality, and phase issues all affect sound quality. On top of that, the listening room changes the sound by boosting or canceling certain frequencies and adding reflections, leaving its own acoustic imprint. DSP can apply correction signals to counteract these errors, ideally canceling them. Speakers can be measured during production, and issues like uneven frequency response and phase problems can be corrected digitally. Because individual speakers vary slightly, DSP coefficients can be fine-tuned for each unit room, and speaker interactions can also be addressed. For example, floor-standing speakers produce reflections from the floor that cause comb filtering, which DSP can correct. Adaptive systems can dynamically adjust for room effects. The speakers emit signals to cancel unwanted reflections, compensating for low-frequency delays, amplitude and phase errors, and floor reflections. Room correction begins with on-site analysis. A test signal is played, a microphone at the listening position measures the speaker room response, and software generates room-specific correction coefficients. The result is a smart loudspeaker that corrects both its own imperfections and acoustic anomalies from its placement in a particular room. DSP can improve the quality of recorded audio by reducing or removing unwanted noise. It can distinguish between noise and music, allowing removal of clicks, pops, hum, tape hiss, or surface noise without affecting the music. Advanced techniques, including AI-based methods, can even restore missing signal caused by tape dropouts. Noise removal usually involves two steps: detecting and removing impulsive noise like clicks, and reducing background noise. Advanced techniques, including AI-based methods, can even restore missing signal caused by tape dropouts. Interactive graphical tools help locate clicks. A declicking program analyzes the surrounding sound and synthesizes a replacement signal. Simple methods like sample and hold create a flat plateau, while linear interpolation connects valid samples with a straight line. More accurate interpolation uses a model of local signal characteristics, analyzing a few or even hundreds of samples. Automatic declicking algorithms must distinguish between actual clicks and short musical transients. When multiple recordings of the same signal exist, errors are easier to spot, but the recordings must be precisely time-aligned. Background noise removal starts by splitting the audio into frequency bands and analyzing each band. The noise is fingerprinted using silent or low-amplitude portions of the recording. An inverse function based on the fingerprint removes the noise. For steady-state noise, the system compares the energy in each frequency band to the noise profile and decides where processing is needed. Some original noise is often kept to maintain a natural sound. Advanced algorithms estimate a clean audio signal and use a masking curve, so only noise not hidden by the music is removed, minimizing artifacts. DSP can reduce hiss from analog tapes, wind noise from outdoor recordings, hum from machines, or background noise from speech in critical recordings. Proper use of noise removal can make a recording sound better than the original. However, excessive or incorrect processing can degrade the audio. Even a small reduction, like 10 to 15%, can improve quality, but overprocessing can create unwanted effects, sometimes affecting the music itself rather than just the noise. Thank you for watching till the end. To better understand each video, make sure to watch the previous ones. Some may serve as prerequisites for the next. If you have any questions or opinions, feel free to leave a comment. Until next time, subscribe and stay curious.